For 8 minutes and 20 seconds, Earth would continue as if nothing had happened. Daylight would still touch the oceans, gravity would still hold the planet in orbit, and the final warmth of the sun would cross space toward a world that had already lost its star. Then, without warning, daylight would end everywhere. Earth would leave its orbit in a straight line. Plants would fall silent, oceans would freeze beneath a growing shell of ice, and even the atmosphere would eventually settle onto the ground as frozen air. Yet deep below the surface, life might continue beside the heat of the planet itself. If this journey into permanent night sparks curiosity, leave a like, subscribe for more calm science stories, and share this video with someone who enjoys the mysteries of space. Thank you sincerely for spending this time here. What time is it where this is playing, and where in the world is it being heard? Leave a comment below. Now, the final sunlight is approaching Earth, and the story begins. For 8 minutes and 20 seconds, nothing changes. The sun has vanished, yet Earth continues beneath an ordinary sky. Morning light still spills across continents. Solar panels still produce electricity. Leaves still absorb photons. The moon still shines with borrowed light. Oceans still glitter. Clouds still cast shadows. And every clock beneath the open sky continues measuring a world that appears unchanged. The disappearance itself has already happened, but the news of it has not arrived. Across the distance between the sun and Earth, light still carries the final image of a star that no longer exists. Gravity, too, still reaches the planet exactly as before. Earth remains in orbit, moving through space at nearly 30 kilometers each second, held along its curved path by the influence of a missing sun. This brief delay is not a trick of perception. It is a consequence of distance and of the finite speed at which information moves through the universe. Sunlight requires little more than 8 minutes to cross the gulf between the star and the planet. Any change in the sun's gravitational field also travels outward at the speed of light. Until that change arrives, Earth has no physical way to respond. The planet cannot know that its central star is gone. For those final minutes, the solar system continues as a delayed image of itself, each world obeying conditions that are already out of date. The familiar sun in the sky is not the sun as it exists at that moment, but the sun as it was minutes earlier. This is always true, even in ordinary times. Every sunrise is a view into the recent past. In this impossible event, that small delay becomes the boundary between normal life and permanent night. The thought experiment begins with an event that known physics does not permit. Matter does not simply vanish. And the sun is far too large for any quantum process to remove it from one location and place it elsewhere within any meaningful time. Its real future is slower and far more violent. Billions of years from now, it exhausts the hydrogen in its core, expands into a red giant, alters the inner solar system, and makes Earth uninhabitable long before the final stages of its life. But a sudden disappearance creates a cleaner question. It removes the sun without explosion, warning, debris, or any outward blast, leaving only the consequences of absence. The first of those consequences is silence. There is no flash. There is no sound crossing space. There is no dark wave visible on the horizon. The last sunlight arrives exactly as earlier sunlight did, and then there is no more. At the end of the delay, the sun does not dim gradually. Its disk disappears from the sky. Day becomes night in an instant, not because Earth rotates away from the light, but because the light itself has ended. At that same moment, the gravitational message reaches Earth. The sun's pull is no longer present, and the orbit loses its center. An orbit is not a fixed path carved into space. It is a continuous fall. Earth moves forward while the sun's gravity bends that motion inward, producing a curve that repeats year after year. Remove the inward pull and the curve ends. Earth continues along the direction it is already moving, following a straight line tangent to its former orbit. The planet does not stop. It does not drop downward. It does not drift slowly away as though released from a weak tether. It departs at orbital speed, carrying the moon, the atmosphere, the oceans, and every living thing into interstellar space. The moon remains bound to Earth because Earth's gravity remains. Satellites continue orbiting for the same reason. The local structure of the planet does not collapse. Only the larger relationship with the sun is broken. The change in direction is immediate. Yet at first it is almost impossible to feel. People standing on the surface do not sense a sudden shove. The ground does not lurch. Earth's motion has always been smooth, and the new straight path is smooth as well. The most obvious sign is the sky. In regions where the sun had been visible, darkness arrives at once. In regions already experiencing night, there is no sunrise to come. The line between day and night ceases to move, because day no longer exists. The moon also becomes dark once the last sunlight reflected from its surface reaches Earth. Depending on the moon's position, that change follows quickly, leaving no bright companion overhead. The planets fade on different schedules. Each one continues reflecting light from the vanished sun until the final sunlight reaches it, and Earth continues receiving those reflections until they cross the remaining distance. Jupiter may appear normal for some time after Earth has already lost the sun. Its light is a record of an earlier solar system. The farther a planet lies from the sun and from Earth, the longer light is a record of an earlier solar system. The farther a planet lies from the delay can become. For a while, the night sky displays a scattered sequence of after images. One world disappears, then another, each fading according to geometry and distance. The solar system does not go dark all at once. It goes dark in layers. Stars remain, because their light comes from far beyond the lost sun. The Milky Way remains as a faint band. Distant galaxies remain as dim patches visible through telescopes. The universe does not vanish with the solar system's central star, but the scale of the darkness changes. Without moonlight or twilight, the natural night becomes much deeper than any ordinary night on Earth. The glow of the galaxy offers only a weak illumination, less than a full moon. Human settlements still produce light. Electrical grids continue operating for a time. Power plants do not depend on direct sunlight, and stored fuels remain available. Cities remain visible from orbit, because every hemisphere is dark. Windows, roads, factories, and emergency systems burn against the black surface. For a short period, civilization creates islands of brightness beneath a sky that has lost its greatest source of light. Yet even before temperatures fall, the first biological crisis has already begun. Photosynthesis stops with the final photons. Plants no longer receive the energy needed to convert carbon dioxide and water into sugars. Marine algae and microscopic plankton at the surface of the oceans face the same interruption. The vast majority of natural productivity on Earth depends directly or indirectly on this process. Food webs do not collapse in 8 minutes, but their foundation loses power at once. Stored energy remains inside seeds, roots, trunks, animals, soils, and oceans, allowing life to continue temporarily. Oxygen also remains abundant. The atmosphere contains an immense reserve, far more than animals and microorganisms could consume in a short span. Breathing does not become difficult that night, or the next, or for many generations. The first fear is darkness. not suffocation. The greater danger develops through cooling and the slow failure of ecosystems. Still, during those opening minutes, the planet offers no warning of what is coming. A person indoors may notice only a flicker as daylight disappears from a window. Instruments register the loss of solar radiation. Observatories confirm that the sun's disk is gone. Satellites record the end of the solar wind after another delay determined by the speed of charged particles already travelling outward. Communication systems fill with reports that no institution is prepared to interpret. The event is impossible, yet its effects are plain. Every explanation that depends on cloud, eclipse, sensor failure, or atmospheric disturbance fails within moments. The Sun is absent from every location at once, and Earth is no longer following its orbit. The realization spreads faster than any physical catastrophe on the ground. There is no impact zone and no safe side of the planet. No nation remains in daylight. No season offers protection. The entire world has entered the same night. Beyond the atmosphere, Earth continues along the line it inherited from its final instant in orbit. The planet is now a rogue world, though almost none of its inhabitants yet understand the scale of the journey. In the first hour, the surface still holds nearly all the warmth it possessed before the disappearance. Oceans do not freeze, forests do not collapse, cities do not immediately fail. The world is physically familiar, but its future has been severed from every pattern that once defined it. Sunrise, summer, harvest, climate, and orbit have all ended together. The first 8 minutes, therefore, become the last ordinary interval in Earth's history. A quiet stretch in which every system continues under the influence of a star that is already gone. When that interval closes, the planet does not merely lose light. It loses the centre around which its days, years, climates, and nearly all surface life have been arranged. The darkness that follows is only the first visible sign. At the instant the final sunlight reaches Earth, the planet loses more than a familiar star in the sky. It loses the force that has shaped its path for billions of years. Until that moment, Earth has been moving forward while continuously falling toward the Sun, its motion bent into a vast curve that repeats as an orbit. The disappearance of the Sun removes the inward pull, but it does not remove Earth's speed. The planet therefore continues in the direction it was already travelling, no longer circling a centre, no longer returning to the same region of space after each year. Its path becomes a straight-line tangent to its former orbit, a line carrying oceans, mountains, cities, and the moon away from the place where the solar system once held together. Nothing on the surface feels like a violent release. There is no sudden wind produced by motion through space, because space offers almost no resistance. There is no sideways fall, no jolt strong enough to throw bodies from the ground. And no immediate change in weight. Earth's gravity remains, holding the atmosphere, the seas, and everything on the surface. The moon remains bound to Earth as well, though its orbit begins to change slowly because the missing sun no longer perturbs the Earth and moon together. The entire pair departs as a small gravitational system of its own, moving through the dark at roughly the speed Earth once carried around the sun. In human terms, the speed is enormous. In the scale of the galaxy, it is modest. One motion added to several others already underway. Even before the sun vanishes, Earth is not standing still in space. The solar system travels around the centre of the Milky Way, and the galaxy itself moves relative to neighbouring galaxies and the larger cosmic structure. The loss of the sun changes one layer of motion, not all of them. Earth keeps the momentum it already possesses from every larger journey. The result is not a simple escape into a fixed background, because there is no absolute stillness against which the planet can be measured. It is more accurate to say that Earth stops following the Sun and begins following a new path through the galaxy, shaped only by whatever gravitational influences remain. In the first hours, those influences are subtle. The other planets still exist, but without the Sun they too move away along their own tangent lines. Each world leaves in a different direction based on where it happens to be in its orbit. Mercury departs fastest. Having moved through the deepest part of the Sun's gravitational well, Venus follows another line. Mars, Jupiter, Saturn, Uranus, and Neptune become separate wanderers, scattered by the geometry of the moment. The solar system does not explode outward like fragments from a blast. It unthreads. Every orbit opens into a path, and the old arrangement stretches apart. Some moons remain with their planets. Asteroids continue according to their own motions. Comets that once travelled on long loops no longer return. The carefully ordered structure that has endured since the birth of the Sun becomes a widening field of independent bodies, each carrying the record of its final position and speed. For Earth, the Sun's disappearance also ends the meaning of a year. A year has always been the time required for one orbit around the Sun. Without that orbit, calendars continue only by convention. Days remain for a while because Earth still rotates. The planet does not stop spinning when it leaves its path. Sunrise disappears, but the rotation continues beneath permanent darkness. Clocks can still divide time, and old calendars can still mark dates. Yet the astronomical cycle beneath those systems is gone. Seasons vanish in a deeper sense. They are no longer waiting to return. The tilt of Earth's axis still exists, but there is no sunlight arriving from different angles as the planet moves around a star. The poles and equator become equally removed from direct solar energy. Geography still affects how quickly regions cool, but not because of summer or winter. The planet has entered a climate with no seasonal source. As Earth moves farther from the vanished centre, its former location becomes an empty point in space. There is no glowing marker left behind. The distance grows quickly, though the change is hard to picture from the ground. After 1 second, Earth has travelled tens of kilometres along its new course. After 1 minute, it has moved thousands. After 1 hour, the distance becomes greater than the span of many nations. Yet there is nothing outside the atmosphere that makes this motion visible. The stars do not stream past. Instruments that once used the Sun as a fixed reference must be recalibrated. While navigation systems tied to orbital predictions begin producing errors that grow with every hour. The equations still work, but their central mass has vanished, forcing every forecast of planetary position to be rebuilt from the final known motions of the departing worlds. The distances are too vast. Constellations appear nearly unchanged, and even precise instruments need time to detect the slight shift in perspective. The sense of stillness remains, though the entire world is crossing space without a central star. The Moon offers one of the few nearby markers. It continues circling Earth, reflecting no sunlight, visible only through artificial illumination or faint background glow. Tidal forces continue because they arise mainly from the Moon's gravity, but the solar contribution disappears. Ocean tides become simpler and generally weaker, though the oceans themselves are beginning a much larger transformation from cooling. The Moon's orbit may gradually evolve under the changed conditions, but it does not immediately fly away. Earth and Moon share nearly the same motion around the former Sun, so both lose the solar pull together. Their mutual bond remains stronger than the distant influence of the missing star ever was across the small gap between them. This shared departure makes the planet less a solitary rock than a dark double system, a world and its companion moving through interstellar space. The long-term route is uncertain because the galaxy is not empty. Stars, gas clouds, dark matter, and the central mass of the Milky Way all contribute to the gravitational landscape. Earth does not travel along a perfectly straight line forever. Its path is straight only in the immediate sense. After the sun's pull vanishes, over immense distances, the galaxy bends that path. The planet may settle into a new orbit around the galactic centre, one slightly different from the sun's former route. It may pass through regions with more stars or fewer, through thin clouds of gas, or through long stretches where no close encounter occurs. The chances of striking a star directly are extraordinarily small because even crowded regions of the galaxy contain vast spaces between objects. A near encounter is more plausible over very long periods, though still uncertain. A passing star could alter Earth direction, accelerate it, slow it, or in rare circumstances capture it into an orbit. Such an event would depend on exact speed, distance, and geometry. Capture by a single star is difficult because energy must somehow be lost or transferred. Yet interactions involving multiple bodies can create pathways that a simple two-body encounter cannot. For the human generations facing the first years of darkness, these possibilities are too distant to matter. The new trajectory is important not because of where it leads soon, but because it has no planned destination. Earth has changed from a planet defined by a star to a rogue planet defined by motion alone. The name suggests isolation. But even a rogue world remains inside larger systems. The galaxy still holds it. Gravity still reaches across immense distances. Earth is no longer orbiting the sun, but it has not escaped the universe. It continues inside a web of forces that are weaker, broader, and slower to reveal themselves. On the surface, the immediate crisis remains darkness and falling temperature. Beyond the atmosphere, another transformation is already complete. The old solar system has become a memory written into the directions of departing worlds. Earth carries one of those directions forward, preserving the exact line of its final moment in orbit. Every second extends that line farther into the dark. What once was a closed path has opened, and the planet will never return to the same year, the same season, or the same place around the sun. Its future is no longer a circle. It is a journey whose shape will be drawn by distant stars, hidden mass, and time itself. The first true night begins without sunset. There is no fading gold at the horizon, no gradual loss of colour, and no familiar transition from day into evening. The sun simply ceases to appear, and the illuminated half of Earth becomes dark almost at once. Clouds that had been bright a moment earlier lose their edges. Mountains disappear into shadow. Oceans stop reflecting the sky. The atmosphere no longer glows blue because there is no direct sunlight left to scatter through it. Across every continent, noon and midnight become almost indistinguishable. The planet still turns, but rotation no longer carries places into morning. It only moves landscapes beneath the same permanent absence. The word night remains useful, yet its older meaning begins to fail. Night was once one half of a cycle. Now it is the condition of the world. The darkness is not complete, because the universe itself is not dark. Stars continue shining from distances so great that their light has been travelling for years, centuries, or far longer. The Milky Way remains as a faint pale structure across clear skies. This background glow prevents absolute blackness, but it is far dimmer than ordinary moonlight. Under a sky free of artificial illumination, the ground becomes difficult to see. Large shapes can still be sensed after the eyes adjust, especially where snow, pale rock, or water reflects the little light available. Forests become nearly featureless. Roads vanish beyond a short distance. The horizon is visible only when it cuts across the brighter band of the galaxy or a dense field of stars. The night is deeper than any natural darkness experienced while the sun existed, because even the darkest nights once carried traces of solar influence. Moonlight, twilight, and reflected light from dust all belonged, directly or indirectly, to the solar system. Now those familiar layers disappear. The moon fades quickly. It produces no light of its own and has always shone by reflecting the sun. Once the last sunlight has struck its surface and the last reflected photons reach Earth, the lunar disk becomes almost invisible. It remains present, continuing its orbit, pulling on the oceans and moving across the stars. But it is no longer a bright object. To unaided eyes, the moon becomes a dark circle against a dark sky. During an occultation, it may briefly reveal itself by blocking stars one after another, a silent absence moving through the background. Its phases end because phases require sunlight. Full moon, crescent moon, and new moon lose their meaning together. The planets also fade, but not at the same moment. Each one receives the final sunlight at a different time, and Earth receives their reflected light after another delay. For a while, the sky preserves scattered echoes of the vanished sun. Venus may disappear early. Mars follows according to its position. Jupiter can continue to shine after Earth already knows the sun is gone, not because it has escaped the event, but because the last light is still crossing the distance. Saturn's rings may remain visible briefly, then darken. The outer planets keep the memory longest, though geometry determines what Earth can observe. The solar system becomes a sequence of delayed messages, every fading point marking news that has crossed millions or billions of kilometers. Eventually, the familiar planets become nearly invisible except through instruments that detect heat. The night sky then belongs almost entirely to objects beyond the old solar system. Observatories no longer wait for sunset, because sunset has become permanent. Telescopes can operate continuously if their power systems survive, and the absence of sunlight removes one source of background brightness. Yet many instruments depend on solar power, heating, supply chains, and human support. Space telescopes lose the sun as an energy source unless they carry nuclear power or can be reconfigured. Satellites continue circling Earth, but their solar panels stop producing electricity. Batteries drain. Communication networks weaken. Weather satellites still observe the planet for a time through infrared sensors, but visible images become mostly black, marked by artificial lights and fading auroras. Human light becomes the dominant visible brightness on the surface. Cities continue shining because power stations, stored fuels, hydroelectric systems, nuclear reactors, and batteries do not fail at the same instant. Streetlights switch on automatically and never receive another dawn signal. Offices, factories, homes, airports, and ports remain illuminated according to emergency priorities. From orbit, Earth appears as a dark sphere scattered with clusters of light. Some regions glow intensely, while rural areas vanish. Yet this human-made constellation begins changing from the first hour. Solar farms stop producing energy. Electrical demand rises as lighting becomes continuous and temperatures fall. Wind continues for a time because atmospheric motion does not stop immediately, though weather patterns weaken as the planet cools. Hydroelectric power remains while rivers flow, but freezing gradually restricts it. Fossil fuels and nuclear reactors become the most dependable large sources, provided maintenance can continue. Electricity is no longer merely a convenience. It becomes a substitute for the missing star. It provides light for work, heat for survival, and power for machines that preserve food and pump water. Every illuminated room represents stored energy being converted into a temporary pocket of order. The darkness also alters behavior before cold becomes the dominant danger. Circadian rhythms, the biological cycles that respond to light and darkness, lose their strongest natural signal. Humans can maintain schedules with lamps and clocks, but animals cannot be managed so easily. Birds that depend on daylight for navigation and feeding become disoriented. Diurnal animals, adapted to activity during the day, face conditions for which they have no seasonal preparation. Nocturnal species initially find a world resembling an endless night, yet their prey, temperature, and feeding cycles begin to change. Insects that navigate by the moon or use polarized light lose their guides. Marine organisms that rise and sink according to daylight continue briefly on internal rhythms, then drift from old patterns. The planet's biological clocks keep ticking, but the signal that once reset them each day has vanished. Artificial light creates small, irregular replacements. Around cities, birds may gather near illuminated buildings. Insects cluster around lamps until falling temperatures end their movement. Greenhouses use electric lights to preserve crops. But the energy demand is immense. A field once illuminated freely by the sun now requires power for every photon needed to sustain growth. Most agriculture cannot continue in its previous form. Darkness becomes an energy crisis spreading through every living system. The atmosphere changes as well. Without solar heating, convection weakens over time. Clouds still exist in the early days because the air retains warmth and moisture, but from below they appear only as darker patches covering the stars. Storms already in progress continue moving. Rain and snow still fall. Lightning remains possible while enough temperature contrast survives. A thunderstorm beneath permanent night becomes one of the few natural sources of sudden visible light, briefly revealing landscapes lost in shadow. Volcanoes, fires, and molten rock also shine more strongly against the darkness. At first, wildfires may continue where they had already begun, and industrial flames remain visible across great distances. Later, as vegetation freezes and weather changes, those lights become rarer. The stars appear sharper wherever the atmosphere is clear. As human activity declines, sky glow from cities diminishes. Constellations emerge from places where they had been hidden for generations. The galactic center, nebulae, and star clouds gain unusual clarity, though their beauty belongs to a world entering catastrophe. The sky offers a strange contradiction. It becomes more revealing at the same moment the surface becomes less visible. The universe seems closer because its faint light is no longer overwhelmed. Yet Earth is becoming more isolated from the source that made surface life possible. Permanent night removes the daily illusion that the sky belongs to the sun. It reveals that the sun was only one star among many, though it was the one star that mattered most. Every distant point continues burning, indifferent to the missing light nearby. Beneath them, civilization spends stored energy to resist the darkness. For a few days, perhaps longer in well-supplied regions, streets remain bright and interiors remain warm. The planet still resembles itself at night, but the resemblance is temporary. One district after another begins to dim as grids fail. Fuel runs short, and power is redirected toward essential systems. The artificial constellations on Earth contract. Darkness spreads not from the horizon, but from the loss of each generator, transmission line, and lamp. Eventually, only isolated centers of power remain, glowing beneath a sky filled with ancient light. The first great transformation is therefore not yet ice or atmospheric collapse. It is the end of brightness as a natural condition. Light becomes scarce, manufactured, guarded, and costly. The night that began without sunset settles across the world, and every surviving flame becomes a small reminder of the star that is gone. The first biological collapse begins in silence. There is no sound when photosynthesis stops, no visible shock moving through forests, fields, or oceans. Leaves do not fall at once. Grass does not turn brown in a single hour. Trees remain upright, crops remain rooted in soil, and vast clouds of microscopic plankton still drift near the ocean surface. Yet the process that feeds nearly every surface ecosystem has ended with the final sunlight. Photosynthesis is the means by which plants, algae, and certain bacteria use light to build sugars from carbon dioxide and water. Those sugars become stored chemical energy, the foundation on which most food webs depend. The moment the sun disappears, this conversion stops everywhere exposed to the loss of light. The effect is immediate at the level of chemistry, even though its consequences take time to spread. The world enters darkness, carrying only the energy already stored within living cells, seeds, roots, wood, soils, animal bodies, and human supplies. For a brief period, life continues by spending its reserves. Plants remain alive because they do not depend only on the sugar being produced at that exact moment. Many hold starches in roots, tubers, stems, and seeds. Trees contain large stores built over years of sunlight. Some species can survive long periods of shade or seasonal dormancy. In ordinary winter, they slow their activity, shed leaves, and wait for light to return. But this darkness is not winter. There is no season ahead, no spring hidden beyond the cold, and no rising sun to restart growth. Every reserve becomes finite. Small plants with high energy demands begin to fail quickly. Crops designed for rapid growth are especially vulnerable. Their metabolism continues, but no new energy enters the system. They consume stored sugars while temperatures fall, and once those stores are exhausted, their cells can no longer maintain themselves. Some plants die within days, others persist for weeks. Large trees may retain enough chemical energy to remain alive much longer, but energy shortage is not their only threat. Water inside their tissues begins to freeze as the planet cools, damaging cell walls and blocking the movement of sap. A giant tree can carry years of stored carbon and still be killed by ice before starvation becomes decisive. The first stage of the crisis therefore looks deceptively calm. Forests remain standing under the stars. Fields remain in place. The green colour does not vanish immediately because pigments survive after photosynthesis has stopped. Yet every leaf has become an engine without fuel. Stomata, the tiny openings that normally exchange gases with the air. Close as metabolism slows and temperatures drop, the flow of carbon through the biosphere weakens. Growth ends. Flowers stop developing. Fruits no longer ripen in the ordinary way. Seeds that require light remain dormant, while seeds that germinate in darkness may begin using their reserves only to encounter a frozen surface and no future source of energy. Agriculture fails not because every plant dies at once, but because the cycle that replaces harvests is broken. Existing grain, stored food, livestock, and preserved crops become more valuable with each passing day. No open field can produce another season. Indoor farming offers a narrow exception. Artificial lamps can provide the wavelengths needed for photosynthesis, and heated greenhouses can protect crops from the cold. Yet sunlight once illuminated the entire planet without a human power system. Replacing even a tiny fraction of that energy requires vast amounts of electricity. Every kilogram of food grown under lamps competes with heating, water treatment, communication, medicine, and industrial survival. The problem is not whether plants can grow under artificial light, They can. The problem is whether civilization can generate enough reliable power to keep meaningful agriculture alive while the world freezes. In the early months, carefully managed facilities may produce vegetables, algae, fungi, and fast-growing crops. Underground farms near nuclear or geothermal power could continue far longer. But the surface system that once fed billions has ended. Livestock face the same narrowing supply. Animals can live for a time on stored grain, hay, and processed feed. But those reserves cannot be renewed at the needed scale. Grazing animals find frozen plants that no longer grow back. Poultry and pigs depend on feed chains that collapse as transport and agriculture fail. Fishing also changes rapidly. At the ocean surface, phytoplankton lose light and stop photosynthesizing. These microscopic organisms form the base of many marine food webs. Tiny grazers consume them, fish consume the grazers, and larger animals depend on the fish. The surface ocean therefore begins losing productivity almost at once, though death spreads unevenly. Some plankton sink, some enter resting states, and some survive briefly on stored energy. Marine animals continue feeding on what remains, but each level of the food chain draws down reserves that no longer refill. Coastal ecosystems, coral reefs, and shallow seas are hit particularly hard because they are closely tied to sunlight. Coral reefs depend on symbiotic algae living within coral tissues. Without light, the partnership fails, and cooling soon compounds the damage. Kelp forests stop growing. Seagrass meadows weaken. The ocean does not become empty overnight, but its sunlit layers begin a long biological shutdown. Oxygen remains, and this is one of the few early mercies. Plants and algae are major producers of atmospheric oxygen, but the atmosphere already contains an enormous supply. Humans, animals, fungi, and microorganisms continue consuming oxygen through respiration, and fires consume additional amounts. Even so, the total reserve is so large that suffocation is not an immediate danger. The fall of oxygen would unfold over timescales far longer than the first human crisis. Most people would die from cold, hunger, infrastructure failure, conflict, or disease long before breathable oxygen became scarce. Carbon dioxide would gradually rise as respiration and decay continue without the balancing pull of photosynthesis. But cooling and the collapse of biological activity complicate that trend. Frozen soils slow decomposition, oceans absorb gases, many organisms die, then decay only where temperatures and microbes allow it. The atmosphere changes, but not in the simple way of oxygen vanishing overnight. The more immediate loss is productivity. The sun has stopped paying the daily energy cost of life at the surface. Every animal now survives by consuming energy captured before the disappearance. Herbivores eat the remaining plants. Carnivores eat the herbivores. Scavengers feed on the dead. Microbes break down what remains. The food web becomes a one-way descent through stored energy, with no broad process to rebuild what is used. Some ecosystems endure longer than others. Forest floors contain roots, fungi, insects, and organic matter that can support slow activity for a time. Deep lakes retain warmth and may shelter organisms beneath ice. Caves host communities that already live without sunlight, though many still depend on nutrients carried in from the surface. The crucial distinction is between darkness and independence. Living in darkness does not mean living without the sun. A cave animal may never see light, yet its food can still come from plants above. A deep-sea fish may swim below the reach of sunlight, yet it may eat matter that once fell from productive surface waters. When photosynthesis ends, these hidden dependencies are revealed. Energy captured in the bright world has been moving downward through ecosystems for countless generations. Now that flow begins to weaken, Humans face the same truth. Supermarkets, warehouses, refrigerators, silos, and fuel tanks appear to contain separate supplies. But nearly all of them are delayed forms of sunlight. Grain is sunlight stored in seeds. Meat is sunlight transferred through plants and animals. Wood, coal, oil, and natural gas are ancient sunlight locked in chemical bonds, though fossil fuels cannot be eaten and can only support food production indirectly. The disappearance of the sun does not erase these stores. It turns them into a final inheritance. Survival depends on how carefully they are used, how long power can be maintained, and whether communities can shift towards systems that do not require direct solar energy. Fungi can grow on stored organic matter. Algae can grow under artificial light. Chemically powered microbes can live without light at all. Yet none of these options can quickly replace the global web of fields, forests, and oceans that once transformed sunlight into food. The first days, therefore, carry a strange stillness. The world is dark, but it has not yet become barren. Leaves remain on branches. Animals still move. Food remains on shelves. The atmosphere remains breathable. Life appears present everywhere, but the great engine beneath it has stopped. From that moment forward, the surface biosphere is living on memory, spending the energy of vanished days beneath a sky that will never brighten again. The darkness alone does not kill the surface. The cold does. During the first hours after the sun disappears, Earth still carries an immense store of heat. The oceans, soils, buildings, forests, and atmosphere have absorbed solar energy over years and centuries, and the planet's interior continues releasing warmth from below. Air temperatures remain within familiar ranges in many places. Rivers still flow. Rain still falls from clouds that formed under the old climate. Yet the balance has changed completely. Before the disappearance, Earth constantly radiates heat into space, but sunlight replaces much of what is lost. Once the sun is gone, the outward flow continues while the incoming supply falls to almost nothing. The planet begins cooling immediately, not because space sends cold inward, but because Earth is losing energy and receiving no comparable return. The fastest changes occur near the surface, where air and soil exchange heat directly with the dark sky. Clear regions cool more quickly than cloudy ones because clouds temporarily slow the escape of infrared radiation. Oceans cool more slowly than land because water can store a great amount of heat. Coastal areas therefore remain less severe at first, while continental interiors and high plateaus fall rapidly below freezing. The first night is unlike any previous winter night because it has no sunrise to interrupt it. Temperatures decline through the hours and continue declining through what would once have been morning. Buildings lose heat through walls and roofs. Roads begin to ice. Lakes develop thin skins of frozen water. Plants already weakened by darkness encounter cold severe enough to rupture tissues and block the movement of sap. The atmosphere still circulates, carrying warmer air toward colder regions and mixing the remaining energy across the globe. But every exchange only redistributes a supply that is steadily shrinking, within days. The average surface temperature approaches the freezing point of water. This global average hides extremes. Some tropical oceans remain relatively warm, especially at depth, while exposed land in polar and continental regions becomes far colder. Storm systems continue because temperature differences still exist, and in some places those differences may briefly intensify. Warm ocean water releases heat and moisture into colder air, feeding heavy snowfall. Rain changes to sleet, then to snow. Coastlines become lined with expanding ice. The familiar geography of climate begins to dissolve as the entire planet moves toward a state once limited to its coldest regions. The pace of cooling is rapid at first because a warm Earth radiates more energy than a cold one. As temperature falls, the rate of heat loss slows. The planet does not plunge toward absolute cold at a constant speed. The early decline is steep, then gradually becomes more measured. After the first week, much of the surface is frozen, but further cooling takes longer. The atmosphere, oceans, and crust continue releasing energy, and each layer delays the next stage. Snow and ice spread across continents. Their greater importance is insulation. Snow traps pockets of air and slows heat exchange with the ground. Ice forms a barrier between cold air and warmer water. These effects do not prevent freezing, but they change where and how quickly it advances. Human survival during this period depends less on distance from the equator than expected. Tropical regions begin with warmer air and water, giving them an advantage, but that advantage is temporary. Without sunlight, the equator receives no special heating. High-latitude communities are often better prepared for cold, with insulated buildings, heating systems, winter clothing, and established practices for operating in freezing weather. Yet even the best prepared cities rely on fuel deliveries, electrical grids, transport networks, and maintenance crews. The cold deepens while those systems face rising demand and growing failure. Pipes freeze and burst, diesel thickens, batteries lose capacity. Roads become blocked by snow and abandoned vehicles. Water treatment plants struggle as intakes freeze and power becomes unstable. Emergency shelters fill rapidly, and every structure with dependable heat becomes a center of survival. Fires provide local warmth, but fuel is limited and smoke becomes dangerous in sealed spaces. Urban forests, furniture, abandoned buildings, and stored timber may be burned. The flames are bright against the permanent night, yet they accelerate the consumption of resources that cannot be renewed. Nuclear power offers one of the strongest remaining sources of continuous energy. Reactors do not require sunlight, but they depend on cooling systems, skilled operators, replacement parts, secure fuel handling, and functioning grids. Some facilities continue operating through the first months, supplying heat and electricity to nearby settlements. Others shut down safely when support systems fail. Hydroelectric stations work while water continues flowing, though ice and falling precipitation gradually reduce their value. Fossil fuel plants operate where coal, oil, or gas can still be delivered. Wind turbines may continue turning during the early atmospheric transition, but icing, maintenance problems, and weakening circulation limit them. The atmosphere itself reacts in complex ways. Warm air can hold more water vapor than cold air, so cooling forces moisture to condense. Clouds thicken in some regions, and snowfall removes water from the air. As the surface freezes, evaporation weakens. The atmosphere gradually becomes drier, even as snow accumulates on the ground. Weather does not stop at once. Winds continue, storms move, and pressure systems remain. But the main engine that once drove them has ended. Solar heating created contrast between day and night, land and sea. Equator and pole, those contrasts begin fading. The atmosphere moves toward a quieter state, though the path includes violent local events as warm oceans release their remaining energy beneath frigid air. Blizzards may sweep across continents. Sea fog forms where open water meets freezing conditions. Hurricanes and tropical storms weaken without warm sunlight to maintain ocean heat, but existing systems can persist briefly before losing their source. Beneath the changing sky, the ground becomes an archive of disappearing warmth. Frost penetrates soils from above. Roots freeze. Burrowing animals retreat deeper. following the last habitable temperatures downward. Insects become motionless. Reptiles, dependent on environmental heat, fail quickly. Mammals and birds burn stored fat at unsustainable rates as food vanishes and cold intensifies. Hibernating species may survive longer if they can remain insulated, but their shelters eventually cool and their future food sources are gone. Life withdraws into caves, burrows, basements, tunnels, mines, and the lower floors of large structures. Depth becomes protection, because rock changes temperature slowly, a few meters underground. Daily and seasonal variation has always been smaller than at the surface. Now that stability becomes essential, existing mines, subways, military facilities, research stations, and deep storage sites offer temporary refuge. Their walls retain heat, and their distance from the surface reduces exposure to wind. Yet even underground communities require ventilation, water, food, sanitation, and power. The cold outside advances through every wall, pipe, and shaft unless energy is continuously supplied. By the end of the first month, the world above has become broadly hostile. Many rivers are sealed by ice. Smaller lakes are frozen across their surfaces. Sea ice spreads far beyond former polar limits. Snow covers regions that once knew only rain. The average temperature continues falling, and many exposed areas reach conditions that ordinary infrastructure was never designed to withstand. Still, Earth is not uniformly frozen. The deep oceans hold most of their heat. Geothermal regions remain warm. Volcanic landscapes release steam into the night. Hot springs flow beneath curtains of ice. Near active faults and volcanic systems, heat from the planet's interior reaches the surface strongly enough to slow the freeze. These places become increasingly important, but they are scattered and often dangerous. Yellowstone, Iceland, East African rift zones, volcanic islands, and other geothermal regions offer natural warmth. Yet they cannot shelter the entire population. Their value lies in local energy, warm ground, liquid water, and the possibility of generating electricity. Away from them, every settlement is spending stored fuel to resist a planetary trend. The first great cooling therefore reveals the difference between weather and climate in its most extreme form. Weather continues for a while as the atmosphere rearranges old heat. Climate changes because the source that sustained the system is gone. Each day becomes colder, though the rate slowly eases. The surface moves toward freezing through millions of separate losses of warmth. A room cooling after power fails, a lake sealing under ice, a forest stiffening in the dark, a city grid dimming beneath snow. The planet remains active, but its activity turns inward. Heat leaves the air, retreats into water, sinks into rock, and survives longest where the surface can no longer reach it. Earth has not yet become a frozen world, but during these first days it crosses the threshold beyond which the old surface environment cannot return on its own. The cold is no longer an event, it is the new direction of the planet. By the end of the first year, the darkness has become ordinary, but the cold has moved beyond anything once considered an extreme season. The average surface temperature has fallen toward roughly 70 degrees below 0 Celsius, with some regions warmer and others colder. At such temperatures, exposed skin freezes quickly. Most machinery fails without constant heating, and ordinary buildings become brittle shells around empty rooms. The oceans are sealed beneath ice. Rivers have stopped. Snow no longer behaves like the soft weather of winter, because the air has grown too cold and dry for frequent storms. Much of the surface lies silent beneath a hard crust of frozen water, wind-blown dust, and abandoned structures. The first panic and the great migrations have ended. Most communities that depended on the open surface no longer exist. Human survival has retreated into a small number of places where heat can still be produced, trapped, and carefully rationed. The surviving settlements are defined less by borders or former wealth than by energy. A city with no reliable heat becomes uninhabitable no matter how large its buildings or how advanced its technology once appeared. A modest underground site near geothermal activity may outlast a capital above ground. Power stations become the centers around which every remaining system is organized. Heat, light, food production, water treatment, ventilation, medicine, and communication all depend on a continuous flow of energy. A failure lasting hours can destroy crops or freeze pipes. A failure lasting days can end an entire settlement. Life becomes a chain of systems with almost no room for interruption. Underground spaces offer the most immediate protection. Mines, tunnels, military facilities, research stations, deep basements, and purpose-built shelters use rock as insulation. The deeper the refuge, the less directly it feels the surface cold. Earth's crust stores heat and changes temperature slowly, so conditions underground remain far more stable than the air above. Yet depth alone does not make a place habitable. Ventilation must remove carbon dioxide and supply oxygen. Pumps must keep water moving. Waste must be treated. Walls must be reinforced against ice, pressure, and structural damage. Every person adds heat, moisture, and biological demand to a closed environment. The underground world is an engineered island sustained by discipline and maintenance. Geothermal regions offer the strongest natural advantage. In places where hot rock lies close to the surface, wells can draw heated water or steam from below. That energy can warm living spaces, generate electricity, melt ice, and support agriculture under lamps. Iceland, volcanic islands, rift zones, and areas around active hot springs become possible refuges, though many are remote or geologically unstable. The heat is not limitless. Wells can cool if overused. Pipes can clog with minerals, and turbines require parts that can no longer be manufactured easily. Even so, geothermal power has one crucial benefit. It does not depend on sunlight, weather, or a fuel delivery crossing frozen continents. It draws from the planet itself, from heat left by formation and from radioactive decay deep within rock. Communities near these sources can build chambers around warm ground, channel steam through insulated pipes, and maintain reservoirs of liquid water long after the surface has frozen solid. Nuclear power provides another path. Reactors can operate without the sun and can produce large amounts of heat from relatively compact fuel. In surviving facilities, electricity is only part of their value. Waste heat from the reactors can warm buildings, greenhouses, water systems, and industrial workshops. Yet nuclear survival depends on knowledge and organization. Reactors require trained operators, stable cooling, secure control systems, and careful handling of fuel and waste. Many plants are never designed to function as isolated lifeboats for decades. Their supply chains once stretch across nations and continents. Replacement valves, pumps, sensors, and specialized materials are no longer easy to obtain. Some settlements may dismantle inactive facilities for parts. Others may simplify systems, reduce output, and operate only one reactor at a time. Small research reactors and naval reactors may become valuable, but only where crews, fuel, and support remain. Nuclear power can preserve a community, yet it cannot restore the old world. It turns survival into a technical project measured in maintenance cycles and inventories. Food becomes the narrowest limit. Stored grain and preserved supplies have carried some groups through the first months. but most reserves are now reduced. Animals raised for meat consume too much feed and space, so surviving agriculture shifts toward organisms that convert energy and material efficiently. Potatoes, grains, legumes, algae, mushrooms, and carefully selected vegetables grow beneath the artificial light. Fungi require no light, but they need organic material, and that material is also limited unless waste streams are recycled. Algae can produce protein and oxygen, though they require controlled water, nutrients, and illumination. In some settlements, vats replace fields. Plant roots grow in water or inert material rather than soil. Human waste, dead plant matter, and chemical nutrients circulate through closed systems. Nothing is casually discarded because every carbon atom, mineral, and litre of water has value. Agriculture becomes less like farming beneath an open sky and more like life support inside a spacecraft. Earth itself has become a wandering vessel, and each heated refuge is a smaller vessel within it. Water is abundant in frozen form but difficult to use. Ice must be mined, melted, filtered, and kept from freezing again. Geothermal sites may have direct access to warm groundwater. Other settlements rely on nuclear or fossil heat. Producing liquid water competes with heating and food production. Pipes run through insulated corridors, and leaks are dangerous because spilled water can freeze into solid barriers. Humidity must be controlled. Too much moisture produces ice on walls and ventilation systems. Too little dries skin, damages lungs, and increases the risk of fire in enclosed spaces. Fire remains one of the great threats underground. In a sealed habitat, smoke and toxic gases can spread quickly, while evacuation into the surface cold may be impossible. Materials are chosen to resist flame, corrosion, and extreme temperature. Social life changes under these conditions. Large populations are difficult to support, and surviving groups must make decisions around energy budgets rather than old expectations. Every new child, greenhouse, laboratory, and heated room increases demand. Medical care becomes narrower as supplies run out and complex equipment fails. Infections are dangerous in crowded habitats. Mental strain grows beneath unchanging artificial light and low ceilings. Clocks preserve a cycle of day and night even though the planet no longer provides one. Lamps brighten and dim according to schedules. Work shifts regulate sleep, food, exercise, and maintenance. These rhythms protect health and preserve a sense of time. Without them, the darkness outside could enter the mind as completely as it has entered the world. Contact between settlements becomes rare. Satellites have failed or fallen silent, and long-distance cables are damaged by cold, ice, and neglect. Radio may still connect isolated communities, but power and equipment limit its reach. Travel across the surface is dangerous and expensive. Vehicles require heated fuel systems, cold-resistant lubricants, insulated cabins, and dependable navigation. A breakdown far from shelter is usually fatal. Aircraft are difficult to maintain and require runways kept free of ice and frozen debris. Subsurface tunnels may connect nearby facilities, while some coastal communities use passages beneath ice or travel through caverns warmed by geothermal activity. Most human groups become islands separated by distances that were once crossed casually. Above them, the old cities remain as frozen monuments. Towers stand in darkness, windows broken by temperature stress and wind. Roads disappear beneath ice and drifting snow. Vehicles sit where they stopped during the first evacuations. Libraries, museums, warehouses, and homes preserve objects in the cold, but reaching them is hazardous. Salvage expeditions move through these ruins to collect metals, medicine, tools, seeds, and machine parts. The surface cold slows decay. turning cities into vast storage vaults. Yet their contents are finite. Every expedition removes something that will not be replaced. Survivors gradually shift from using the remains of civilization to maintaining a smaller world of their own. The first year, therefore, marks a boundary. Before it, survival still depends largely on stored supplies and emergency response. After it, survival belongs only to systems capable of continuing without the sun. The surface has become a place to cross, mine, and endure briefly. The living world has moved downward, closer to the heat inside Earth. Human existence persists, but it is no longer spread across continents beneath an open sky. It survives in chambers of light surrounded by frozen rock, sustained by reactors, hot water, recycled air, and the careful conversion of energy into time. Outside, the planet continues into interstellar darkness. Inside, every functioning pump and every growing leaf becomes evidence that the disappearance of the sun has not yet ended the human story. Long after the continents have frozen and the last open rivers have disappeared, the oceans remain the greatest reservoirs of warmth on Earth. Their surfaces turn to ice, but the transformation is slow because water stores heat more effectively than air or rock. The upper layers cool first, releasing energy into the atmosphere until they reach the freezing point. Then a thin sheet forms across calm bays, lakes, and sheltered seas. Waves break it, winds push it into ridges, and currents carry fragments into warmer water. But the cold continues. Over weeks and months, separate fields of ice expand and join. The polar caps spread toward the equator. Tropical seas, once warmed by direct sunlight, lose their final advantage. Eventually, nearly every ocean lies beneath a continuous frozen shell. From above, Earth appears smooth and pale, a dark wandering planet wrapped in ice. Yet this frozen surface does not mean the oceans have vanished. It means they have become hidden. Water behaves in an unusual and life-preserving way as it freezes. Most liquids become denser as they cool, but water reaches its greatest density just above the freezing point. Colder water remains nearer the surface, where it turns into ice. The solid form is less dense than the liquid below, so it floats. This simple property prevents the oceans from freezing from the bottom upward. Instead, a lid forms across the surface, and that lid gradually thickens. Ice is also a poor conductor of heat compared with liquid water or rock. Once a substantial layer develops, it slows the escape of warmth from the ocean below. The colder the surface becomes, the stronger the temperature difference across the ice. But the growing thickness makes heat harder to transfer. Freezing continues, yet the process becomes slower with depth. The upper ocean turns solid first. Beneath it, water remains liquid, dark, and increasingly cut off from the atmosphere. The thickness of the frozen shell grows over decades, centuries, and far longer. But it may never reach the deeper seabed while Earth continues producing internal heat. The ocean floor is not cold in the same way as the surface. Heat rises through the crust from radioactive decay and from energy left over from the planet's formation. Most of this flow is weak when spread across the entire globe, but it is persistent. In some places, it becomes concentrated along volcanic ridges, fractures, and regions where tectonic plates separate. There, seawater seeps into cracks, is heated by hot rock, and returns through hydrothermal vents. These vents release mineral-rich water into the deep ocean, forming warm local environments beneath a world of ice. Even without the sun, the seafloor continues generating heat. It does not produce enough energy to keep the entire ocean warm, but it can delay complete freezing for an immense span of time. The result is a layered planet. At the top lies an atmosphere growing thinner and colder. Beneath it rests a shell of ice that may eventually become kilometers thick. Below the shell lies liquid water, preserved by insulation and by the slow warmth rising from Earth's interior. At the bottom, the crust remains geologically active in places, creating narrow zones where temperature, chemistry, and water meet. These hidden oceans are among the most stable environments left on the planet. They are dark, pressurized, and far removed from the conditions that once defined surface life. But they are not empty. Even before the sun disappears, most of the deep ocean exists beyond the reach of sunlight. Photosynthesis is limited to the upper layers where enough light penetrates. Below that zone, organisms survive on matter that sinks from above, on other animals, or on chemical energy released from the seafloor. When surface productivity ends, the steady rain of organic material declines. Dead plankton, fish, plants, and animals continue sinking for a time, creating a final pulse of food. Scavengers gather, bacteria break down the remains. Deep ecosystems consume this inheritance slowly, but much of it is finite. Species that depend on surface-derived food begin to disappear as the supply weakens. The ocean does not preserve every form of marine life simply because liquid water remains. Most fish, whales, corals, and open ocean food webs are still linked to the sun through long chains of dependence. Their decline unfolds over years and generations, unevenly and often beyond human observation. The ice above blocks light and contact. Entire ecosystems vanish in silence. Yet the deep ocean contains another path. Near hydrothermal vents, microbes use chemosynthesis. Instead of capturing sunlight, they obtain energy from chemical reactions involving substances such as hydrogen sulfide, methane, hydrogen, and iron. These compounds rise from beneath the crust or form when hot water reacts with rock. Microbes convert that chemical energy into organic matter, becoming the foundation of local food webs. Tube worms, clams, mussels, shrimp, crabs, and other organisms live around some vents, directly or indirectly supported by these microbes. This system does not require sunlight at the point of production. It depends on geology. As long as water circulates through hot rock and reactive chemicals remain available, life can continue. This independence is not absolute. Some vent organisms may rely indirectly on oxygen produced by ancient photosynthesis and dissolved in seawater. As circulation changes and the atmosphere evolves, oxygen levels in the ocean may fall. Certain communities could decline, while anaerobic microbes, organisms that live without oxygen, become more important. Life adapts not as a single preserved ecosystem, but as a shifting collection of metabolisms responding to a colder and more isolated planet. The hidden ocean becomes a laboratory of survival. Pressure increases with depth, yet deep-sea organisms are already adapted to it. Darkness is complete, yet darkness has always been normal there. Temperature away from vents may fall toward the freezing point, but salt lowers the freezing temperature of seawater, allowing it to remain liquid under conditions that would freeze fresh water. Salts and dissolved minerals become more concentrated as ice forms above, altering circulation and chemistry. Dense brines may sink. Layers develop. Some regions become too salty or chemically harsh for familiar organisms, while others remain stable. The ocean continues moving, though currents driven by winds and solar heating fade. Convection from freezing, salinity differences, geothermal heat, and the shape of the seafloor create slower forms of circulation. Water near the base of the ice cools and becomes dense. Warmer water rises from below. Brines descend. Around vents, heated plumes move upward until they mix with surrounding water. The grand circulation of the former oceans contracts into quieter patterns, but it does not end. For surviving human communities, the ocean becomes both a barrier and a possible refuge. Reaching liquid water beneath kilometers of ice is difficult, yet coastal settlements near geothermal activity may drill downward or use existing tunnels, mines, and volcanic channels. Submersible facilities could theoretically operate beneath the ice, protected from surface cold and supplied by nuclear or geothermal energy. Water is abundant, and pressure can be managed with strong structures. The ocean offers thermal stability compared with the atmosphere above. Its temperatures change slowly, and deep regions may remain near freezing rather than plunging toward the far lower temperatures of the surface. But survival there requires extraordinary engineering. Habitats must resist pressure, corrosion, leaks, and isolation. Food production still needs energy. Oxygen must be generated or extracted. Waste must be recycled. A failure in darkness beneath thick ice allows little chance of rescue. The ocean is not a ready-made shelter. It is a place where shelter could exist if technology, power, and maintenance endure. Over centuries, the ice shell thickens and the distance between surface and sea increases. Former coastlines lose meaning. Mountains and plains become buried beneath snow and frozen gases. Above the oceans, the ice records layers of dust, ash, and material settling from the cooling atmosphere. Below, the liquid water remains protected from the most severe cold. The contrast becomes one of the defining features of the rogue Earth. From space, the planet appears lifeless. No cloud patterns reveal open seas. No sunlight reflects from blue water. No vegetation marks the continents. Yet beneath the frozen exterior, a vast world remains mobile, chemical, and alive in places. Heat leaks through the crust. Minerals dissolve into water. Microbes divide around vents that have never seen sunlight. Some may continue for millions or even billions of years, depending on the persistence of geological activity and the stability of the ocean. The surface catastrophe does not reach them as a moment. It reaches them as a gradual change in chemistry, circulation, and falling food. There is no awareness of the missing sun, because sunlight was never part of their environment. The oceans therefore preserve more than liquid water. They preserve the possibility that a planet can remain biologically active after losing its star. Earth becomes a world with two histories. The upper history is written in ice, ruin, and the disappearance of surface life. The lower history continues in darkness, shaped by rock, water, and chemical energy. Between them lies the frozen shell, sealing away the last great habitable realm. The planet is no longer blue, but deep beneath its pale surface, the oceans endure. The atmosphere does not remain a permanent shelter above the frozen world. For years after the sun disappears, it still surrounds Earth as an invisible ocean of gases, pressed against the surface by gravity and stirred by currents left over from the old climate. Nitrogen remains the largest component, oxygen remains plentiful, argon, carbon dioxide, water vapor, and traces of many other gases still move through the cold darkness. Yet an atmosphere is not guaranteed simply because a planet has gravity. It also depends on temperature. Gas molecules move faster when they are warm and slower when they are cold. As Earth loses heat, those molecules surrender energy. The air becomes denser, quieter, and less able to remain in the same familiar state. Eventually, the cold crosses thresholds at which substances that once floated freely overhead begin to condense, freeze, and fall. The first great atmospheric change comes from water. Much of it has already left the air during the early cooling, forming clouds, snow, frost, and thick deposits of ice. Warm air once carried large amounts of moisture, especially above tropical oceans. Cold air cannot hold the same quantity. As the temperature falls, water vapor condenses and descends, leaving the atmosphere increasingly dry. Clouds become thinner in some regions and heavier in others, then gradually diminish as open liquid water disappears from the surface. Snow still falls where enough vapor remains, but over time the sky loses the endless cycling of evaporation and rain that once shaped weather. The atmosphere begins to resemble a depleted reservoir, with each storm removing material that is no longer easily returned. Carbon dioxide follows a more complicated path. Some freezes onto the surface in the coldest regions, while some remains mixed in the air for longer. It can dissolve into ocean water beneath the ice, react with minerals, or become trapped in frozen deposits. Volcanic activity continues releasing small amounts from below, but the balance has changed. Without sunlight, there is no active surface biosphere drawing carbon dioxide into plants, and without warm oceans, there is far less exchange with the atmosphere. The gas becomes part of a slow chemical rearrangement rather than a living cycle. Methane, once produced by wetlands, animals, and microbes, also changes. Biological sources collapse at the surface, while some deep microbial sources persist. In the frigid air, methane reacts slowly and may eventually condense under sufficiently low temperatures. These minor gases alter first, but they are only the beginning. The main transformation arrives when the atmosphere itself becomes cold enough for oxygen and nitrogen to stop behaving as permanent gases. Under ordinary Earth conditions, oxygen boils at a temperature far below the coldest natural weather, while nitrogen requires an even lower temperature to liquefy after the sun vanishes. However, the surface continues cooling for decades and beyond. The decline becomes slower with time, yet it does not stop while Earth continues radiating more energy than it receives. In the deepest cold, the atmosphere approaches the conditions found in laboratories where air is turned into liquid. The difference is scale. No machine is compressing a sample into a metal container. The entire planet is becoming the container. Oxygen reaches its condensation point before nitrogen under comparable pressure. At first, the change begins in the coldest places, likely at high elevations, polar regions, and surfaces that radiate heat efficiently into space. Invisible gas becomes droplets. A strange dew forms on frozen ground, not made of water but of liquid oxygen. It gathers in hollows, coats exposed surfaces, and flows into cracks. Where temperatures fall farther, it freezes into a pale solid. The colour may be faintly blue in thick deposits, though the darkness hides most of it. This is not ordinary precipitation formed from warm clouds and cooling air. It is the collapse of a planetary atmosphere onto the ground. The sky is literally losing part of its substance. Nitrogen follows at lower temperatures, because nitrogen makes up most of the atmosphere. Its condensation transforms the planet more dramatically. Liquid nitrogen forms where the cold is severe enough. Pooling across lowlands and flowing over ice, it may fall as droplets, mist, frost, or crystalline snow depending on local pressure and temperature. Winds weaken as the air thins, but before they fade they can carry clouds of condensed gases across the surface. Valleys collect liquid air. Basins become temporary lakes of nitrogen mixed with oxygen and argon. Ridges and ruins grow coated in frost made from the former sky. The atmosphere that once seemed vast reveals its limited mass. Spread over Earth, it appears immense. But once condensed, it forms only a relatively shallow global layer compared with the oceans. Its collapse is visually dramatic yet physically finite. Much of the gas settles into low regions, leaving mountains and high plateaus exposed to near vacuum. Pressure falls, sound travels less effectively. Any surviving human habitat becomes more dependent on sealed walls and recycled air, not only because the outside is cold, but because there is less atmosphere left to breathe. The withdrawal of air changes heat loss as well. A thick atmosphere transfers energy through winds and convection. A thin one cannot. Once most gases have condensed, the remaining surface loses heat mainly through radiation and direct contact with frozen deposits. The weather systems that once crossed continents disappear. There are no familiar storms, no broad cloud bands, and almost no wind. Instead, local events occur where condensed gases evaporate near geothermal regions or exposed heat sources. A vent opening through the ice may warm nearby nitrogen and oxygen, creating temporary plumes that rise, cool, and fall again as frost. Around volcanic areas, the atmosphere can partially return in small pockets. Heat boils liquid nitrogen, melts oxygen deposits, and produces transient clouds. These gases drift outward and refreeze, creating a slow circulation between warm ground and cold surroundings. The planet develops a new kind of weather powered from below rather than above. Near active volcanoes, hot gases escape through fractures and meet the collapsed atmosphere. The contrast can be extreme. Steam freezes, carbon dioxide forms dry ice, sulfur compounds crystallize, nitrogen fog rolls across black rock before settling again. Such places are dangerous, unstable, and chemically harsh, yet they remain among the few surface regions where gas, liquid, and solid states continually exchange. Elsewhere, stillness dominates. The idea of breathing from the snow becomes less like fiction and more like engineering. Oxygen frozen on the surface can be collected, warmed, purified, and released into sealed habitats. Nitrogen can be used to maintain pressure and protect against fire. In principle, the atmosphere has not been destroyed. It has merely changed phase. The same molecules remain on Earth, trapped in deposits that can be mined like ice. Surviving communities with sufficient power could gather these materials and rebuild breathable air inside enclosed spaces. Yet the process requires energy at every stage. Frozen gases must be located, extracted, warmed, compressed, and stored. Any leak releases air into surroundings where it quickly condenses again. The outside world no longer supports breathing even for a moment. A broken seal becomes as dangerous as exposure to space. The surface becomes a vacuum chamber scattered with frozen oceans and buried reservoirs of air. The atmosphere may not collapse completely. Geothermal heat, volcanic emissions, and the planet's remaining internal warmth can sustain a faint layer of gas near some regions. Small amounts of hydrogen, helium, neon, and other volatile substances may behave differently. Some escape more easily to space over long periods. Others remain trapped in ice. The exact sequence depends on pressure, composition, local temperature, and the changing thickness of the frozen deposits. The process is not a single global snowfall occurring on one night. It is a gradual retreat, beginning in the coldest places and spreading as the planet cools. For long intervals, Earth may have patches of denser air near warm regions and almost none elsewhere. The boundary between atmosphere and surface becomes uneven, mobile, and tied to hidden heat below. From orbit, the planet no longer shows the soft haze that once marked its atmosphere. The edge appears sharper, clouds vanish, weather ceases to reveal motion. The world resembles a sealed sphere of ice and rock, but the materials of its former sky remain laid across the ground. Nitrogen rests in frozen plains. Oxygen gathers in shaded basins. Carbon dioxide forms hard deposits. Water lies locked in glaciers above oceans that still move beneath their lids. Every major layer of the old environment has changed place. Sea has become roof, air has become snow, warmth has retreated into stone. This atmospheric fall marks one of the deepest stages of Earth's transformation. Darkness removes the light, cold stills the surface, and finally the sky itself descends. What once surrounded every mountain and filled every breath becomes part of the landscape, waiting in frozen silence for heat that may never return. Far below the frozen atmosphere and the sealed oceans, life continues in places that have never depended on daylight. These environments are not untouched by the disappearance of the sun, but they are separated from its first and most destructive effects. Around hydrothermal vents on the ocean floor, heat rises from fractures in the crust. Seawater descends into porous rock, warms near magma or hot mineral layers, and returns carrying dissolved chemicals. When this heated water meets the cold ocean, minerals precipitate and build towers, chimneys, and branching structures around the vent openings. The process creates narrow zones of energy in a world without light. Long before the sun vanishes, these places already support communities based on chemistry rather than photosynthesis. Microbes use compounds such as hydrogen sulfide, hydrogen, methane, and iron as sources of energy. Through chemosynthesis, they transform inorganic material into organic matter, forming the base of food webs that can include tubeworms, mussels, clams, shrimp, crabs, and many smaller organisms. The exact species differ from one vent field to another, but the underlying pattern remains the same. Rock, water, and chemical imbalance replace sunlight as the first step in the chain. This gives vent ecosystems an unusual advantage after the surface world collapses. Their primary energy source remains available as long as geology continues. The disappearance of the sun does not cool the mantle, stop radioactive decay, or end the circulation of water through hot crust. Tectonic activity continues. Magma still rises. Minerals still react. For the organisms closest to these processes, the change above arrives slowly and indirectly. The surface ocean stops producing food, so the rain of organic material from above declines. Oxygen levels may shift. Currents change as the ocean freezes and the atmosphere collapses. Yet the vent itself continues releasing heat and chemicals. The local ecosystem contracts, adapts, and rearranges, but it does not necessarily end. Some communities depend partly on oxygen that was originally produced by photosynthesis. That oxygen remains dissolved in the ocean for a long time, but it is no longer being renewed at the surface. As animals and microbes consume it, the deep ocean may become increasingly low in oxygen. Species with high oxygen demand weaken first. Anaerobic microbes, which live without oxygen, become more important. Some use sulfate, carbon dioxide, or other chemicals in their metabolism. Life shifts toward forms that need less energy and tolerate harsher conditions. The resulting biosphere is smaller, slower, and less visible than the old one, but it may be more durable. Chemosynthetic life does not require a bright planet. It requires a continuing flow of chemical energy, liquid water, and enough stability for cells to repair themselves and reproduce. Earth still provides all three beneath the ice. Hydrothermal vents are not the only refuges. Microbes live deep within the crust, inside pores and fractures where groundwater carries dissolved minerals. Some inhabit rock far below the seafloor. Others survive beneath continents, isolated from sunlight for geological spans. These deep organisms gain energy from reactions involving hydrogen, sulfur, iron, and carbon compounds. They grow slowly because energy is scarce. A single generation may take far longer than it would near the surface. Their world is quiet, pressurized, and poor in nutrients, yet it is protected from storms, seasons, radiation, and sudden changes above. The loss of the sun makes the surface hostile, but deep rock remains almost indifferent. Temperature underground changes very slowly. Water can remain liquid in fractures. Radioactive elements continue releasing energy. Chemical reactions between water and certain minerals can produce hydrogen, creating a fuel for microbes. This hidden biosphere may contain fewer organisms than the former surface world, yet its survival prospects stretch across immense time. The boundary between living and non-living matter becomes harder to observe as activity slows. Microbes may enter dormant states, reducing metabolism until conditions improve. Some form spores or protective structures. Others remain active at extremely low rates, using just enough energy to maintain cell membranes and repair damage. In a frozen rogue planet, persistence matters more than growth. A thriving ecosystem is no longer necessary for life to endure. A thin population scattered through warm cracks can preserve biology across millions of years. The surviving organisms do not know that the sun is gone. They have no eyes, no sky, and no memory of daylight. Their environment is defined by pressure, temperature, mineral gradients, and the flow of water. The catastrophe that ends forests and cities reaches them only as a change in chemistry. Fewer nutrients sink from above. Water circulation becomes slower. Some vents weaken as tectonic regions evolve. Others open in new places. Life follows these shifting sources as it always has, spreading where conditions permit and disappearing where they do not. The scale is local. A vent field can support dense life while the surrounding seafloor remains almost empty. When one vent closes, organisms must reach another or die. Many cannot travel far. Larvae and microbial cells drift with currents, but currents beneath the ice may be slower and more isolated. Entire communities vanish when their heat source fails. Survival at the planetary level comes from repetition. Thousands of vents, fractures, warm sediments, and deep aquifers create many separate chances. Some fail early, others persist. The biosphere becomes a network of buried islands, disconnected yet sustained by the same internal planet. This hidden endurance changes the meaning of a dead world. From space, Earth appears frozen and still. No vegetation alters its color. No weather marks its atmosphere. No ocean reflects a star. Instruments passing at a distance might classify it as a rogue planet with a thick ice shell and little visible activity. Yet beneath that shell, microbes divide in darkness. Chemical energy moves through cells. Organic molecules are built, broken down, and reused. Life continues without any outward sign. The planet is not alive in the broad, luminous way it once was, but neither is it sterile. The difference is buried beneath kilometers of ice and rock. The persistence of these organisms also reveals how deeply surface life has been tied to the sun. Most animals, plants, and microbes depend directly or indirectly on photosynthesis. Even creatures living in caves or deep ocean water often consume material that began as captured sunlight. Vent communities are different because their primary production begins with geology. Their existence shows that life can occupy an energy system separate from the star above. This does not mean such ecosystems are independent of every surface condition. Ocean chemistry, pressure, and available oxidants still reflect the history of the whole planet, but their core energy source comes from below, and that allows them to outlast the collapse of the surface biosphere. Over long spans, Earth's internal heat gradually declines, radioactive isotopes decay, tectonic activity weakens, the mantle cools. These changes occur over billions of years, not human lifetimes. The deep ocean may remain partly liquid for an extraordinary period, especially where ice insulates it and geothermal heat rises steadily. Vents may continue opening and closing as the crust evolves. Microbial ecosystems can persist through these cycles, though their total energy supply becomes smaller with time. The rogue Earth therefore carries a biological clock that is no longer set by sunrise or orbit. It is set by the cooling of the interior. Life lasts as long as rock remains warm enough, water remains liquid, and chemical gradients continue to form. The surviving organisms may also alter their surroundings. Microbes deposit minerals, produce gases, and change the chemistry of vent fluids. Their activity can leave traces in rock, creating layers and patterns that endure long after individual cells die. If Earth is ever found by another civilization, these mineral signatures may reveal that life persisted after the sun vanished. If the planet later approaches another star and begins to warm, dormant cells or active deep communities could become the source of a second expansion. Meltwater could open new habitats, chemical nutrients could rise toward the surface. Evolution could begin exploring environments that had been sealed for ages. Such a recovery is uncertain. But the possibility exists because life has not been erased. It has retreated to the places where sunlight was never essential. The most enduring Earthlings are not the largest, most intelligent, or most visible. They are the smallest organisms living around hidden heat. Forests fall, oceans freeze, and the atmosphere settles onto the ground. Yet microbial life continues in the dark, sustained by a planet that still carries fire within itself. Beneath the frozen crust, Earth still carries a reservoir of heat that the vanished sun did not create and cannot take away. This internal warmth is smaller than the energy once received from sunlight, yet it is persistent, ancient, and deeply woven into the structure of the planet. Part of it remains from Earth's formation, when dust, rock, and metal collided, compressed, and melted under the force of gravity. Part of it comes from radioactive elements whose atoms continue to decay within the mantle and crust, releasing energy into the surrounding rock. Together, these sources keep the deep interior hot, even while the surface drifts toward temperatures far below anything known in the former climate. The contrast becomes extreme. Above, nitrogen and oxygen settle as frost across a silent world. Below, rock remains soft, mobile, and in places partly molten. The planet appears dead from space, but its interior continues changing. Heat rises slowly, carried by conduction through solid rock, by the movement of hotter material within the mantle, and by magma that forces its way through fractures. This upward flow is weak when spread across the entire surface, yet over geological time it shapes continents, feeds volcanoes, and preserves liquid water beneath the ice. The heat left from formation begins with violence on a scale the present Earth no longer remembers. During the planet's early growth, countless bodies strike and merge. Their motion becomes heat. As Earth grows larger, gravity compresses its interior. Dense metal sinks toward the center, releasing additional energy as the planet separates into layers. The core forms, the mantle surrounds it, and a crust cools at the surface. Much of that original heat escapes during the first ages, but not all of it. The deep Earth is large, insulated, and slow to cool. Billions of years later, some of that early energy remains trapped within. Radioactive decay adds a continuing supply. Isotopes of elements such as uranium, thorium, and potassium transform into more stable forms, releasing heat in the process. This decay occurs throughout the crust and mantle. It does not depend on sunlight, atmosphere, or life. It continues according to the properties of atomic nuclei, indifferent to the disappearance above. The heat from these elements helps drive mantle convection. the slow circulation of rock over immense spans of time. Hotter material rises, cooler material sinks. The movement is measured not in storms or currents visible to the eye, but in centimeters per year. Yet over millions of years it moves continents, opens oceans, closes basins, and carries heat toward the surface. The core provides another important source. Earth's inner core is solid metal surrounded by a liquid outer core. As the planet cools, the inner core grows gradually, and the freezing of iron releases latent heat. Chemical differences between solid and liquid metal also help drive motion in the outer core. That motion sustains the magnetic field, a shield once important against charged particles from the sun. With the sun gone, the solar wind eventually disappears, but the magnetic field does not immediately vanish. The core continues turning and convecting according to its own energy. Auroras fade because there is no longer a stream of solar particles to excite the upper atmosphere. Yet the invisible magnetic structure can remain for a long time. It becomes another sign that the planet still possesses internal motion beneath its frozen exterior. For human survivors, the most useful expression of this heat appears where it reaches shallow depths. Geothermal regions become natural lifelines. Hot springs, geysers, volcanic fields, and warm aquifers reveal places where the crust is thin, fractured, or close to magma. In the old world, these areas are unusual landscapes. In the rogue world, they are among the few places where liquid water can remain near the surface, and where heat can be harvested without transporting fuel across frozen continents. Wells drilled into hot rock can bring steam or heated water upward. Turbines convert some of that energy into electricity. The remaining heat can warm habitats, melt ice, and maintain enclosed farms. Even modest geothermal gradients become valuable. In many regions, temperature increases with depth. A mine or borehole descending far enough can reach rock warmer than the frozen surface, though the exact depth varies from place to place. The deeper the habitat, the more difficult construction becomes, but the more stable the temperature may be. Geothermal energy is not unlimited or effortless. A reservoir can cool if heat is removed faster than the surrounding rock replaces it. Water can carry dissolved minerals that clog pipes and damage turbines. Earthquakes can fracture tunnels. Volcanic regions can release toxic gases or erupt. Yet the fundamental source remains available for far longer than stored coal, oil, or gas. Its timescale is geological. This makes geothermal heat the closest thing the rogue Earth has to a native star. It does not illuminate the sky or warm every continent. It rises in scattered places, local and uneven, but it can sustain islands of habitability. The same heat preserves the deep oceans. Beneath thick ice, geothermal flow warms the seafloor from below. In most places the effect is slight, but the ice above greatly slows the escape of energy. Around hydrothermal vents, the concentration is stronger. Water circulates through hot rock, carries minerals upward, and feeds chemosynthetic life. These ecosystems survive because Earth continues to cool slowly rather than becoming instantly inert. The planet's internal heat therefore supports both technology and biology. A human settlement may use steam to power lamps and pumps. A microbial community may use chemical energy produced by the interaction of hot water and stone. Both depend on the same hidden furnace, though at very different scales. Tectonic activity also continues, at least for a long time. Plates move because of forces within the mantle and the sinking of cold oceanic crust into the interior. The disappearance of the sun alters surface temperature and ice loading, which can affect stress within the crust. But it does not halt plate motion at once. Earthquakes still occur. Volcanoes still erupt beneath ice. In some places, Lava reaches the surface and creates temporary lakes of molten rock surrounded by frozen gases. The heat boils nitrogen, melts oxygen frost, and turns buried water into explosive steam. These events are dangerous, yet they reveal that the planet remains geologically alive. A volcanic eruption beneath kilometers of ice can melt enormous cavities, creating hidden lakes and channels. Some may remain liquid for long periods, warmed by magma and sealed from the vacuum above. Such environments could become refuges for microbes or, with enough engineering, for human communities. The internal heat also slows the complete freezing of the crust itself. Rock at the surface becomes intensely cold, but deeper layers remain far warmer. The boundary between frozen and warmer rock moves downward only slowly. Heat continues flowing upward, and the thickness of the frozen shell grows until the outward loss balances the internal supply. The exact balance changes over time as radioactive elements decay and the interior cools. Eventually, geological activity weakens. The mantle becomes less mobile. Volcanism declines. The core cools further. But this future lies far beyond the first years, centuries, or even millions of years after the sun's disappearance. Human civilization, if it survives at all, faces immediate limits of machinery, food, population, and knowledge long before Earth's internal furnace becomes exhausted. For deep microbial life, however, the long decline matters. Their future is tied to the persistence of liquid water and chemical gradients. As internal heat fades over billions of years, habitats contract toward the warmest fractures and deepest reservoirs. Life becomes thinner, slower, and more isolated. Even then, complete extinction is not certain until water freezes everywhere or chemistry can no longer support metabolism. Earth's interior gives the biosphere time, perhaps an immense amount of it. This hidden warmth changes the meaning of the planet's journey. Earth is not a cold stone carrying only the remains of a former world. It is a layered engine, still releasing energy as it moves between the stars. The surface tells a story of absence, but the depths tell a story of delay. Heat from formation, radioactive decay, core growth, mantle motion, and volcanic activity continues after sunlight ends. It holds oceans open beneath ice, feeds microbes around vents, and gives isolated human settlements a narrow path forward. The sun once dominates nearly every visible process on the surface, but the planet has always possessed another source of energy, quieter and older, hidden beneath every continent and ocean. In the permanent night, that inner fire becomes the final inheritance of Earth. Once Earth leaves the vanished sun, it becomes a rogue planet, a world no longer bound to any star. The name suggests a body cast into emptiness, but the journey is not through a true void. Earth remains inside the Milky Way, moving among stars, gas clouds, dust, dark matter, and the weak pull of distant masses. Its new path begins as the straight continuation of its former orbit, but the galaxy gradually bends that path into a broader motion around the galactic center. The planet is no longer circling the sun, yet it still belongs to a larger system. Earth carries the speed it once had in orbit, roughly 30 kilometers each second, and adds that motion to the speed the solar system already possessed around the Milky Way. These directions combine into a new trajectory. The exact route depends on the instant of disappearance, on where Earth stood in its orbit, and on how that motion aligned with the sun's galactic path. A difference of season would produce a different road through space. The planet's future is therefore determined by a moment that can never be repeated. The line it follows is not aimed toward any destination. It is simply the consequence of momentum and gravity. In the first years, Earth remains near the region where the solar system once existed. The other planets are also departing, each along a path inherited from its own orbit. Their separations grow. Some may pass relatively near one another, but most drift apart without collision. The Sun's former family becomes a loose spray of worlds crossing the galaxy. Earth may retain the Moon. Jupiter may keep many of its satellites. Smaller bodies may form temporary pairs or scatter through more complicated encounters. Yet the central architecture is gone. There is no single object to hold the system together, and no shared year by which its motion can be measured. After centuries. The original arrangement is difficult to reconstruct from position alone. After millions of years, the former planets may be spread across vast distances, each changed by its own encounters and internal evolution. Earth's surface remains frozen during this travel. The lack of sunlight allows no broad thaw, and the atmosphere lies mostly condensed onto the ground. The planet is dark in visible light, but it still emits infrared radiation from internal heat. A distant observer with sensitive instruments might detect a faint warm signature around geothermal regions or cracks in the ice. That glow is weak compared with a star, but it prevents Earth from being entirely invisible. The planet may also retain a magnetic field and a thin cloud of gas near warmer regions. These features make it more than a silent ice sphere. It remains geologically active, chemically complex, and biologically inhabited in hidden places. Yet from the distances between stars, those details are almost impossible to see. The Milky Way is wide enough that even a planet moving quickly requires immense time to cross it. At tens of kilometers each second, Earth covers hundreds of millions of kilometers in a year, but a light year is far greater. A journey comparable to the width of the galaxy would take far longer than 1 billion years at such a speed. The exact distance travelled depends on the curved galactic orbit and on gravitational encounters, but the voyage is measured in geological eras. Continents would shift beneath the ice. Mountain ranges would erode or be reshaped by tectonics. The magnetic field might weaken or change. Human civilization, if any part of it persisted, would face countless generations before the planet crossed even a modest fraction of the galaxy. Space appears crowded because the sky is filled with stars, but the apparent closeness is deceptive. The gaps between stars are enormous. A rogue planet can travel for millions of years without passing near one. Direct collision with a star is extraordinarily unlikely. Stars occupy only a tiny fraction of galactic volume. Even a passage through a dense stellar region would still involve long distances of emptiness. More likely encounters involve the extended gravitational influence of a star rather than its surface. A star passing within a few light years could alter Earth's path slightly. A closer passage could change its speed and direction, or disturb the Moon's orbit. Such encounters are rare, but the long journey gives rare events more opportunities to occur. The galaxy does not guide Earth toward a new home. It exposes the planet to a sequence of possibilities, most distant and weak, a few capable of rewriting the future. Gas clouds may be crossed along the way. These clouds are thin by terrestrial standards, yet over long periods they can deposit dust and atoms onto the planet. Some particles may carry organic molecules, others may contain minerals unlike those common on Earth. The amounts are small, but geological time allows subtle layers to accumulate. Cosmic rays continue passing through the surface, breaking molecules and altering exposed ice. Without a thick atmosphere and strong magnetic shielding everywhere, radiation reaches farther into the frozen crust. Deep life remains protected by kilometers of water, ice, and rock. Nearer the surface, any surviving organisms must depend on artificial shielding or burial. The exterior is open to interstellar space, while the interior remains sealed from it. The galactic tide, the combined gravitational influence of the Milky Way, also acts continuously. It helps shape Earth's broad route around the centre of the galaxy. Passing stars and giant molecular clouds add smaller disturbances. Over millions of years, the Moon's orbit could be altered. Though Earth's gravity may continue holding it unless a close encounter intervenes. If the Moon were eventually stripped away, tides in the hidden ocean would weaken, and the stability of Earth's axial tilt might change. Yet with no sunlight, the climatic importance of that tilt would be small. Earth would become more solitary, carrying no large companion through the dark. A sufficiently close stellar encounter could produce several outcomes. The simplest is deflection. Earth approaches a star, accelerates as it falls through the star's gravity, then leaves on a new path. The planet remains unbound. A more complex interaction involving a star and one or more planets could exchange enough energy for capture. Earth might enter a wide, elongated orbit, though capture is difficult without a third body to carry energy away. The new orbit could pass close to the star and far into darkness at another. It could be stable, temporary, or chaotic. Earth might also be captured by a binary star, where two stellar masses create more pathways for gravitational exchange. None of these outcomes is assured. Most rogue planets may wander without ever finding a new star. The galaxy offers opportunity through scale, not through intention. For life beneath the ice, the voyage remains mostly unnoticed. Hydrothermal microbes continue responding to local chemistry. They do not sense changing constellations or the slow approach of a distant star. Their world is measured in gradients of heat, sulfur, hydrogen, and pressure. Human descendants, if technology and society endure, would understand the journey through instruments. They could map nearby stars, calculate future passages, and watch constellations shift across thousands of generations. The sky would become a record of motion. A star once faint might brighten over centuries, another might drift away. The galactic band would change angle as Earth followed its new orbit. No sunrise would mark time, but the movement of the universe would remain visible to those who could observe it. The frozen surface might preserve traces of the old civilization with unusual clarity. Cities buried in ice, machines sealed in cold, and archives protected underground could survive far longer than under weather and biological decay. Tectonics and radiation would eventually damage them, but some structures might endure for millions of years. Earth would carry not only living microbes and possible human communities, but the physical memory of a starlit world. Every road, fossil, and layer of sediment would belong to a period before the disappearance. The planet itself would become an archive travelling between stars. Its journey would not be a straight crossing from one sun to another. It would be a long galactic drift, curved by gravity and interrupted by rare encounters. Nothing dramatic would happen. The stars would remain distant. The ice would thicken or stabilize. Internal heat would decline slowly. Life would persist in hidden regions if energy remained. Yet every distant star would represent a possibility, however small, that the path could change. Earth would move through darkness not toward a promised destination, but through a field of chances spread across immense time. The old orbit had been predictable, repeating, and closed. The new path is open, shaped by forces too distant to feel, and futures too long to witness. Earth becomes a vessel without navigation, carrying oceans beneath ice and life beneath oceans, while the galaxy slowly decides where its wandering line will bend next. A second dawn is possible, but it is not promised. For millions or billions of years, Earth may continue through the galaxy as a dark planet with a frozen surface, a buried ocean, and scattered life sustained by heat from below. Then, somewhere along that immense path, a star may begin to grow brighter against the background. At first, it is only one point among many, changing too slowly for any single generation to notice. Over centuries, its motion becomes clear. Over thousands of years, its light strengthens. The frozen world approaches a new source of gravity and energy, and the long night begins to acquire direction. The encounter does not guarantee rescue. Most stars pass too far away to warm Earth meaningfully, and most gravitational approaches end with the planet deflected onto another dark route. Capture by a single star is difficult because Earth must lose some of its motion relative to that star. Without a third body or another mechanism to carry energy away, the planet usually falls inward, accelerates, and then escapes again. A binary star, a system with large planets, or a complicated sequence of close encounters offers more possibilities. Gravity can exchange energy among several bodies, slowing Earth enough to leave it bound. The resulting orbit may be broad, narrow, elongated, unstable, or temporary. Yet across the enormous span of galactic time, even a small possibility becomes part of the planet's future. If capture occurs, the first change comes not as a sunrise but as a gradual increase in radiation. The star grows from a bright point into a steady source of heat. Its color depends on its temperature. A red dwarf gives weaker, redder light and may require Earth to orbit close. A star similar to the vanished Sun offers a more familiar spectrum, but not necessarily a familiar climate. Earth approaches with a surface shaped by ages of freezing. Its atmosphere lies condensed across the ground. Its oceans are sealed under thick ice. Continents have moved, mountains have changed, and the planet may rotate at a different rate. A new star does not restore the old Earth. It begins a new experiment with an ancient world. As light strengthens, the most volatile frozen gases respond first. Nitrogen, oxygen, carbon dioxide, and other compounds begin to warm and change from solid into gas. Frost retreats from exposed rock. Thin clouds form above geothermal regions and then spread as pressure rises. The atmosphere rebuilds itself from the surface upward. Winds return, at first as local movements between warmer and colder ground. Later, they cross continents, lifting dust and carrying vapor through a sky that has been nearly empty for ages. The first weather of the new era is driven by imbalance. Some regions warm quickly under direct light, while others remain locked in shadow or buried beneath deep deposits of ice. The restored atmosphere may be thin, dense, or chemically altered depending on how much gas remains and how much has escaped during the long journey. Oxygen may still be present in large frozen reserves, but it may also have reacted with surface minerals. Carbon dioxide released by warming ice and volcanic activity can create a strong greenhouse effect, trapping heat and accelerating the thaw. The early climate may therefore swing through states unlike anything in the former solar system. Ice does not melt evenly. Dark volcanic rock absorbs light and warms first. Cracks open around equatorial regions or wherever the new orbit produces the greatest heating. Meltwater gathers in basins, flows beneath ice, and refreezes in colder terrain. The thick ocean shell responds from both directions. Heat from the new star attacks it from above while geothermal energy continues rising from below. Lakes form on the surface, canyons fill, glaciers begin to move, grinding across landscapes that have remained still for ages as the shell thins. Pressure changes within the buried ocean. Fractures can release water and gas in towering eruptions. Entire sections of ice may collapse, exposing dark liquid seas to a sky for the first time since the sun vanished. The return of open water transforms the planet, but it also creates danger. Oceans absorb heat and drive storms. Water vapor enters the atmosphere, increasing the greenhouse effect. Snow and rain return. Violent circulation develops between warm seas and frozen continents. The first dawns may pass over a world of fog, steam, broken ice, and deep clouds rather than blue sky. Life beneath the surface encounters these changes slowly. Microbes around hydrothermal vents continue as they have for ages, but the ocean above them begins to circulate more strongly. New chemicals arrive from melting ice and weathered rock. Nutrients long trapped near the surface are carried downward. Some organisms die as temperature and oxygen levels shift. Others spread into newly opened habitats. Dormant cells preserved in ice sediment, or deep fractures may become active when liquid water and energy return. Their survival is uncertain, especially after such immense time. But microbial life is resilient at scales larger organisms cannot match. If even a small living population remains, the thaw offers space for expansion. Chemosynthetic communities no longer need to remain confined to vents. Their descendants can enter warmer waters, shallow sediments, and mineral-rich pools. Evolution begins working with conditions that have not existed for geological ages. Photosynthesis may return only if organisms capable of using light still survive or evolve again from available biology. The old photosynthetic lineages may be gone. If some persist in protected habitats or dormant forms, the new star provides the energy they have lacked. Pigments absorb unfamiliar wavelengths. Organisms adapted to darkness face selection in a bright environment. Some retreat deeper. Others develop new ways to use the light. A biosphere that once shrank toward the interior begins moving outward. It does not recreate the forests, animals, or civilizations of the former Earth. Those belong to a specific history under a specific sun. The new biosphere grows from whatever remains, shaped by altered chemistry, a different star, and a planet transformed by wandering. The orbit around the new star determines whether this recovery lasts. A highly elongated path may produce severe cycles, with brief warm passages followed by long returns to cold. A close orbit around a red dwarf may expose Earth to flares and intense radiation. A stable orbit at a moderate distance offers the gentlest possibility, though stability itself can take ages to confirm. The planet's rotation and axial tilt affect the rhythm of light. It may experience long days, weak seasons, or strange patterns if gravitational encounters have altered its spin. The moon, if it remains, continues shaping tides. If it has been lost, ocean circulation and rotational stability follow different paths. Every part of the second dawn carries the memory of the journey. Evidence of the old world remains beneath the thaw. Frozen cities emerge from ice. Layers of atmospheric snow preserve the chemistry of the collapse. Sediments record the final plankton blooms, the dying surface ecosystems, and the long pause when organic material nearly stopped falling into the deep ocean. Human structures may be crushed, corroded, or scattered by glaciers, but some underground chambers could remain sealed. Archives, machines, and bones may survive as fossils from a civilization that once understood why the sun disappeared but could not follow the planet into deep time. New life, if it becomes complex, may one day encounter these remains without knowing their purpose. It may find metals arranged in impossible patterns, tunnels cut through ancient rock, or chemical traces unlike any natural deposit. The story of the first sun could be reconstructed from geology long after every direct memory is gone. Yet the second dawn may never arrive. Earth may pass star after star at distances too great for capture. Internal heat may fade, habitats may contract, and life may finally end beneath the ice. The thought experiment remains open because the galaxy offers no guaranteed destination. What matters is that disappearance does not lead to one simple outcome. Earth does not instantly become a dead stone. It moves through stages, from delayed sunlight to orbital escape, from permanent night to freezing air, from surface collapse to hidden survival. The planet becomes a vessel carrying water, heat, chemistry, memory, and perhaps life across distances no living surface creature could endure. A new star is only one possible ending, but it reveals the deepest implication of the journey. As long as Earth remains intact and some form of life survives below, the future is not entirely closed. Darkness can last longer than civilizations, longer than species, and longer than continents. Yet it is still a condition rather than a final law. Somewhere ahead, a point of light may grow brighter, ice may begin to loosen, and a world that has forgotten the meaning of morning may turn once more toward a star.